Thank you, Anima. Oh, it's on. Okay, great. Yeah, so our first speaker will be Zachary Ross. He's a professor of geology and the geophysics, sorry, and the William Hurt Scholar here at Caltech. And he is a seismologist who uses AI to better understand earthquakes, which is pretty important here. The title of his talk is Earthquake Science in the AI Era.
Okay. So, as I said, I'm a seismologist. I am interested in pretty much all aspects of earthquake processes. I'm in particular interested in everything from the physical side of this to the hazard side of this. And what I'll talk about today is more focused on the hazard side, but this is a map of the San Francisco Bay Area, and each of these red lines is a fault that runs through the region. And we have to be able to characterize shaking patterns and so forth for various purposes. In particular, within dense urban areas, this becomes increasingly important. And so here is an example of a shaking pattern for a particular scenario earthquake happening on the east side of the Bay Area. We can see that this process here, this wave field that results from this, is incredibly complex. And it turns out that this type of process is really a stochastic process. So this is one kind of realization of a very complex process. And if this happened again, even on the same fault, it might start in a different location. It might last for longer or shorter and so forth. And so we're interested in being able to learn distributions on complex processes like this to be able to better characterize hazards in the urban environments like these. So in particular, we want to be able to learn generative models for these stochastic processes. In my case, this is motivated from my interest in earthquake hazards research, but this applies more generally to other types of stochastic processes. And in particular, the aspects that I think are most relevant here are, number one, being able to characterize shaking patterns in urban areas before an event occurs. So this is kind of like a prior, essentially. We also have what we call earthquake early warning, which is basically real-time forecasting of the ground shaking while an event is unfolding. So as you saw here on my previous slide, where you see the waves take a certain amount of time to travel through the region, just like in this diagram here, if we have an event that nucleates at some point, and if we have sensors that are close by, we can quickly detect this and try to alert the public and so forth before the actual shaking arrives at the sensors or in the urban area. So more recently, I've become interested in trying to do this in the context of the actual ground motions itself. So conditional on what you are observing so far, how can you forecast this ahead? We want to be able to condition this on properties like the soil parameters that we have knowledge of and other types of engineering parameters, the structures and things like this. And ultimately, the kind of setup for this whole thing is dealing with sensor networks that are dynamic, so they're varying in time, they're highly sparse, they are irregular spatially, and that has led us to basically looking at learning on function spaces to be able to do this. And when I talk about what I'm going over today, you can think about it like this, where if here you have an example of a Gaussian process, which many people are probably familiar with, where you have some number of points, a sparse number that you observe this function at. We want to be able to infer the values of that function at other points. This is functional regression, but what we're interested in here is what I'm calling universal functional regression. It's basically trying to learn non-Gaussian stochastic processes and be able to generalize these and so forth in a tractable way. So that's where this is going. So looking at different types of generative models here, if you have finite dimensional generative models, this is very common in vision and things like this, where you have fixed length vectors that you're trying to generate. We can talk about now functional generative models, which deal with infinite dimensional spaces. And so here, for example, with turbulent flow fields around vehicles and so forth. And then I'll put this latter category, which is stochastic processes. And here, to me, this is containing function generation, but it's more than that. It's being able to rigorously satisfy mathematical properties for stochastic processes, being able to evaluate point density and things like that on a finite collection of points within the medium, and be able to do this functional regression task on non-Gaussian processes and things like this. So that's kind of what I'm going to focus on here, some recent work that we've been doing, which really came out of some, like I said, it's come from kind of the earthquake side of things, but we've been moving towards this direction because of our need for it, where we've developed this framework that we call operator flow matching. Flow matching, if you haven't heard of it before, is very similar to diffusion models, where you have a generative model that maps some base distribution, like a Gaussian measure, to some target distribution. So basically here, the difference is that this mapping is done through a vector field that evolves like this, for example, and that vector field satisfies certain differential equations and so forth. But in this case here, we're first of all extending this to stochastic processes, and so treating this in an infinite dimensional setting, and being able to map between a Gaussian process and a target stochastic process in a way that's essentially bijective, so you can go backwards and forwards. And so basically the idea here is that once we train this on a set of observations, we can now freeze this, take this as a prior over stochastic processes, and essentially map a set of sparse observations back into a latent Gaussian process at those same points. We can do, for example, Gaussian process regression in this latent space and then map it back to sample exactly from the posterior. So that's kind of what this is about. The mathematical framework for this is a little messy, but basically we have a continuity equation. This is a weak form of one here, where we have a time-dependent operator GT that we want to be able to learn. And so this is just a continuity equation here, but now extended to the infinite dimensional setting. And basically we want to construct a vector field that's parametrized by a neural operator, so this G theta here. And we're able to do this using essentially this dynamic form of the two Wasserstein distance in order to constrain the difference between these measures. So that's kind of the very quick essence of that. But as part of this work, we've basically shown that we can directly extend this flow matching concept to stochastic processes, which is induced by the Kolmogorov extension theorem from the function space definition with neural operators. So the cool thing about this is that it provides exact tractable likelihood estimation for an arbitrary collection of points, because we're learning in the function space, so it's agnostic to the discretization. And that means that we can compute this likelihood or density going through here, back on the base measure, and mapping it backwards through this. And to compute this divergence term here, we use this Hutchinson trace estimator. And so once we have this, we can freeze it, and we can get a closed form equation for the posterior given noisy and sparse observations of a function at some collection of points. And we can then sample from that directly with things like stochastic gradient Langevin methods. So here is an example of this. So this is after you've pre-trained a model on Navier-Stokes fields, where you now have some ground truth field. We take a very sparse set of points on this field. This is like less than 1% of the points. And we can then do this kind of universal functional regression on the full domain to sample from the posterior that's conditional on those points. So this would be like the mean of that distribution and a couple samples from that distribution compared with some other types of models that are based on neural processes. And this is an example of doing the same thing on a data set of black hole images, where the black hole images have very complex patterns in them due to the swirling effects, and we can still capture these both in the mean and in the individual samples with relatively sparse observations, because it's learning this very complex covariance structure across these non-Gaussian processes. And so this is kind of where this led us from our own work out of need, but basically now we have this kind of framework in place, and we're moving forward with trying to use this for learning the distribution over all these shaking patterns and so forth. And so in seismology, we've been collecting lots and lots of data globally from many large events and so forth. And so we're trying to be able to use this now to be able to generate a whole ensemble of shaking scenarios for urban areas and other places of interest, and be able to capture all these very complex patterns in a much more efficient way. And being able to do this by learning these priors allows us to also do these real-time problems where we can condition the future wave field and so forth on the observations at a sparse number of points. So yeah, that's what I have to share with you today, and maybe if there's time, I'll take a question.
Do we have any questions? No, no questions? Oh, to get through, okay. Sorry.